Good morning all of you. Today we are going to discuss mathematical modeling of mechanical systems. Okay, subject control systems. Okay, so in the last class I have discussed finding the transfer function of electrical networks. Okay, so in this class we will use the electrical networks. Okay, while converting mechanical systems into electrical systems. Okay, so basically the conversion is called analogous systems. Okay, so let us see this also. Okay, so let us see the concept of analogous systems. So what do you mean by analogous systems? See, two system equations of similar form, okay, are defined as a analogous systems. Okay, so which means, see, the advantage of analogous systems are, if the response of one system is known, okay, then the other system response also known without solving it actually. Okay, so that is the advantage of analogous systems. Analogous system means what? See, suppose mechanical system, I have mechanical system and electrical system, right? So the equations of system equations will be in the same form. Okay, so that what will happen if I find the transfer function of electrical system. Okay, okay, so which means what? I find the response of the electrical system. Just if I convert that into the mechanical system, then without solving the mechanical system, okay, I can know the its response. Okay, both are same, which means, right? So let us see the definition. Two system equations of similar form are defined as analogous systems. Okay, two system equations of similar form are called as analogous systems, right? Okay, next we will see other point. What is the advantage actually? The advantage of analogous system is, if the response of one system is known, then the response of the other system is also known without solving it. Okay, so what do you mean by analogous systems? Okay, the major advantage of analogous system is, okay, if the response of one system is known, okay, then the response of other system also known without solving it actually. Okay, so that is the advantage. So in this mathematical modeling of mechanical system, what we are going to do is, okay, we will for given mechanical system, okay, we will write the differential equations for that one. Okay, and also we will convert the differential equations to the electrical equations, then we will find the transfer function. Okay, right. Generally, mechanical systems are converted into analogous electrical systems. Okay, so in this case for given mechanical system, okay, we'll convert into electrical system, analogous electrical system, which means what, the response of the system will be same, okay, even though if converted mechanical to electrical form, right? So let us see what is the advantage, actually advantage of electrical systems, why we are converting mechanical system into electrical systems. So in the last class I have discussed about that, given brief introduction on that. See, in electrical systems, okay, it is very easy to find the transfer function. Why? Because see, for given network, okay, we have number of laws, okay, and formulas, okay, and also parameters are exist in the electrical systems. For example, Ohm's law, Kirchhoff voltage and current law, Thevenin's Norton's theorem, mesh analysis, loop analysis. Okay, so many methods and formulas will be exist in the network analysis. I mean, in the electrical systems, right? So whereas in mechanical system we don't have that much of facility. So what we are doing here? So mechanical system, okay, writing the equation of mechanical system and converting that equations into electrical system, and we'll find the transfer function of that one. Okay, therefore the response, whatever the response we got, transfer from the transfer function, okay, it is same for both mechanical as well as electrical. So then only we are calling mechanical systems are converted into analogous electrical system, which means both are same response, contains same response, right? Okay, we'll see what are the advantages. We'll mention few advantages here. So advantages of electrical system. Okay, advantages of electrical systems. Okay, so let us see the first one. As I told, standard symbols are available, you can say. Symbols are available in electrical systems like passive elements, say resistance, inductance, and capacitance. Okay, so we have a standard symbols like passive elements and active elements also, right? Second point, standard and simple laws are available in electrical systems. Electrical systems, which makes it easier for calculation. Okay. So these are the advantages of electrical systems. Okay, so that's why we are taking mechanical systems are into a analogous electrical systems. Okay, conversation, right? So let us see the concept of mechanical systems. Okay. So see here, I will write mechanical systems, right? So basically mechanical systems are classified into two types. One is translational mechanical systems, another is rotational mechanical systems. Okay, so these categories are classified based on the type of motion of these mechanical systems. Okay, so let us see the classification. Mechanical systems are classified into categories. Okay, based on the type of their motion. Okay, so these are based on the type of the motion of the mechanical systems. Okay, okay, let us see. The first one is translational mechanical systems, and the second one is rotational mechanical systems. So what are they? So mechanical systems are basically classified into two types based on the type of motion, okay, of their motion, right? The first one is translational mechanical systems and second one is rotational mechanical systems. Okay, so let us see the translational mechanical systems. Okay, so will the first one, translational mechanical systems. Okay, so what do you mean by translational mechanical systems? Okay, so in a translational system the motion is along a straight line. Okay, so the motion will be along a straight line, we can say, right? So along a straight line. So let us see. In a translational mechanical systems, the motion is along a straight line. Okay, which means what? These systems involves translatory motion. Okay, so right, so let us, which means these systems or involves translatory motion, that is motion along a straight line or linear motion. Okay, so we'll write that purpose also. These systems involves translatory motion. That means what? motion along a straight line, or we can say linear motion. Okay, now we'll see the variables and elements of the translational mechanical systems. Okay, let us see the variables of the translational mechanical systems. So variables of translational mechanical systems are so I can say the first one is displacement, and the second one is velocity, and the third one is acceleration. Okay. See, so the variables of translational mechanical systems are displacement, velocity and acceleration, right? So basically we'll indicate this one with displacement in terms of x, and this will be v velocity, and this acceleration will be small n. Okay. Right, let us discuss about displacement, velocity and acceleration terms. Okay, so see here, when an object changes velocity, then it accelerates. Okay, which means what? See here, which means what? Acceleration shows the change in velocity in a unit time. Which means what? See here, which means what? What are the units of velocity? Velocity, if I write this one as a v of t, what are the units of this one? Units are meter per second. Okay, now what is the acceleration? Units of acceleration, what is that? So it is become d by dt of velocity, which means what? Meter per second square, right? Now let us see velocity is the time derivative of displacement. Okay, which means what? So v of t is equal to d by dt of x of t. Okay, so which is nothing but I can write dx by dt, right? So what are the units for this one? So velocity units are meter per second. See, displacement is nothing but, see here, in this case displacement is what? See, the distance with direction is called displacement. Okay, so which is represented with x or x of t, the time function x of t. Okay, and the units are meter. Okay, so these are the three terms. Okay, so basic variables used in the mass element. Okay, so let us see the basic elements of translational mechanical systems. Okay, so we'll see basic elements of translational mechanical systems. Okay, right. So the first one is mass element. Okay, so which is represented with m, mass m. Okay, and the second one is damper element. Okay, so it is also called dashpot. Okay, and it is represented with capital P. Okay, and the third element, spring element. Okay, and it is also called stiffness, and it is represented with K. Okay, so these are the basic elements of translational mechanical system. Okay, so we'll see the first one, mass element. So the first one, okay, mass element. Okay, so generally is represented with m, right? So let us see the mass element diagram. Okay, suppose say this is my reference or a valve. Okay, valve. Okay, wait a minute. Now this is my mass element m, which is connected like this. Okay, now in this case, see, we have here a displacement and also in this direction velocity, right? So if I applied external force, say f of t, okay, on a mass, then we will see what happened. And this one is the reference. Okay, so this is the mass element. Okay, see here, so basically it is due to mass m. The basic mass element, okay, is due to mass m, right? And second one is mass stores the kinetic energy of the motion. Okay, so you need to remember this. Mass stores the kinetic energy of the motion. Okay, so in this case, see here, if I consider this as an input and this as my output of this particular mass element, let us see that. Suppose if I consider here input is equal to force, that is, in this case I will write f of t, okay, and output is, say, displacement, or say velocity, right? Sorry. So what is the displacement here? Displacement is nothing but x of t, and the velocity I have taken as a v of t. Okay, so therefore, see, when the force f of t is applied to a mass, then it experiences an acceleration, basically, right? Therefore, by Newton's second law of the motion, we can write F is equal to ma, summation of F is equal to ma. Okay, so we'll see this also. See, when the force F of t is applied to a mass m, then it experiences an acceleration. Okay, therefore by Newton's second law of the motion, so what we will write, that is the summation of F is equal to m into a. Okay, where F is nothing but a force, m is nothing but a mass, and a is acceleration. Okay, so therefore in this case, if I write force, external force applied to mass, okay, element mass m, then I can write this mass into acceleration. Okay, what do you mean acceleration? If we write in terms of displacement, so d square by dt square into x of t. Okay, so if I write this in terms of velocity, then mass into, what is that value? D by dt of v of t. Okay, see the units of this one. So if I consider units of this one, see, generally force, so whatever the force, the units are Newton in SI, right? So if I convert this one, kg by kg meter per second square. Okay, so this one I can write here, force becomes kg meter per second square, right? So this is a conversion here, right? So which is nothing but m means what? Mass means it is nothing but a kg, and here, see here, meter per second square. Okay, so the units of displacement is nothing but what? Meter. Okay, so here see the rate of change of time is twice here, so meter square, right? Now in this case, again, for this one you write this one, sorry, mass means what? Here we have a kg. And see here, what is the velocity units? Meter per second. So I'll write this for meter per second. Again, rate of change of time here. So what is that? Rate of change of time. So again s. So which is nothing but kg meter per second square. Okay. So see here, these are the units of units. All units are equal in both sides, right? So this is the force. Whenever we applied external force to a mass, okay, then so these are the when then it experiences acceleration basically. Okay, so acceleration equations are written here. Okay, mass into acceleration, right? So these are the units. Okay, so clearly we will write the equations. The first one say, okay, the equations will write here in terms of velocity. Okay, so in terms of velocity we will see. Okay, so whenever force applied to a mass, I am naming it Fm, I mean okay, so mass into d by dt, rate of change of time with the velocity, right? Now we'll see B in terms of displacement. Okay, now see, input an external force applied to a mass. Okay, therefore that is m into a, m mass into d square by dt square into x of t. Okay, so x of t is nothing but here what? Displacement. And the units same. What are the units here? Units are kg meter per second square. Here also units are kg meter per second square. Okay. Right. So whenever an external force applied to a mass, okay, we need to write mass into acceleration, right? So this is the Newton's second law. Okay, by using Newton's second law we written these equations. Okay. All right. So before going to second element, damper element, okay, so we will discuss various types of frictions here. Okay, so see, whenever two physical bodies are in motion, then there exists a friction, right? So here we are going to discuss three types of frictions. Okay, that is static friction, viscous friction and Coulomb friction, right? So let us see that. So whenever two physical bodies are in motion, then exists then there exists, you can say, exists a friction. Okay, so it can be three types. So we are going to discuss three types of frictions here. Okay, so the first one is static friction, and the second one is viscous friction, and the third one is Coulomb friction. Okay. So the first, static friction. What is the static friction here? See, static friction is nothing but when the mass, say body, okay, when the mass or body is not in motion, okay, and it always prevents to move from particular place, okay, so it don't want to move from that place, okay. And see here, the direction of the the direction of the static friction always opposite to the body want to move, okay. So that is the static friction. And what is the viscous friction? See, viscous friction is a friction between surfaces and fluids, okay. So this friction is always directly proportional to the velocity, okay. So the first friction, static friction, is related with the mass element, okay, and second one is the viscous friction, which is the damper element, okay. So third friction we will discuss while discussing spring element, third element, right? So just complete these three. I will define this one and this one here, so that so first one I can define static friction. It is observed that only when the body is not in motion and its tendency is to prevent the body from moving. And see, the direction of the static friction is always opposite to the direction in which the body tends to move, okay. See here, static friction is nothing but it is observed that only when the body is not in motion and its tendency is to prevent the body from moving, okay. So the direction of the static friction is always opposite to the direction in which the body tends to want to move, okay. So this is nothing but a static friction, right? Let us see second friction, that is viscous friction. Okay, so what is the viscous friction? It is a friction between surfaces and fluids, okay, and the frictional force is experienced when the body is in motion, okay, and this force is always proportional to the velocity of the body. Okay, so we'll write that also. Here see, it is the frictional force experienced when the body is in motion. Okay, and I can say, and this force proportional to the velocity of the body. Okay, and here the friction is between surfaces and fluid. Okay, right, so these are the two frictions we have discussed here. Right, now we'll see the second element. Okay, the basic elements of translational mechanical system. In that second element, what is that? Damper element, right, or I can say that is dashpot. Okay, which is represented with capital B. Okay, right. Now the symbol of, you can see the element if I connected between so this is called damper element. Okay, represented with B, right? Now the forces applied here, so this is displacement, this is velocity. Okay, so we can write this one as a x1 of t, v1 of t. Okay, and here also we have x2 of t and v2 of t, right, or simply we can say x1 x2 and v1 v2. Now the force is applied, for example force is applied in this direction, f of t. Okay, now let us see. Okay, now we will write the input output equations. In this case input is same force and output is velocity and displacement, right? So let us see. The force, this force I can write like this. Okay, damper force, damping force can write. Okay, F is equal to, now in terms of velocity you can write simply. Okay, so what is that? The damper element B into, okay, Vt. Okay, so B into Vt, right? So which is nothing but I can write in terms of displacement, then B into, what is that? D by dt of x of t, where x of t I am taking as x1 of t minus x2 of t. Okay, x1 minus x2 is nothing but I am taking here x of t, right? So therefore let us see the units here. Okay, so here see the force is taken kg meter per second square. Okay, so see here generally force, the units are Newton. Okay, if you convert these units, it's become a kg meter per second square. Okay, so this one here. Now what about this one? See here the damping coefficient B is called here damping coefficient, or you can say viscous friction coefficient. Okay, so this one B is nothing but kg per second. Okay, into what is the velocity? Meter per second. So what is the value of this one? Kg meter per second square. Okay, so kg meter per second square, same units, right? Now this one same, so here also same, kg per second into, see displacement means meter, and change of the rate of change of time. Okay, so therefore s, what is the value? So kg meter per second square. Okay, so all the units are same here, right? Okay, so I need to mention here also, so where B is nothing but damper element, or I can say here damping coefficient. Okay, or this is also called viscous friction coefficient. Okay, and as you know V of t is nothing but what? Velocity. Okay, and x of t is nothing but displacement. Okay, and that is nothing but here time. Okay, right? Now units are clear here. Now we will write separately the damping coefficient equations when applied to a force to it. Therefore I am writing here the first one, in terms of velocity. What is that? Whenever force, an external force applied to the on the damping coefficient, then what is that? It is becomes B into Vt, right? The velocity, right? Damping coefficient into velocity. Now second, writing the expression in terms of displacement. Okay, so what is that? So same external force applied to a damping coefficient, therefore B into d by dt of x of t. Okay, so where I can write x of t is equal to x1 of t minus x2 of t. Sorry, x2 of t, right? So you need to remember this. These are the equations of damping coefficient or viscous friction coefficient, right? So see here the damper element is to provide resistance behavior in the mechanical system. Okay, such as is same as in the resistance in the electrical systems. Okay, so so this is the damper element equations, right? So third one we'll see the spring element. Third one, spring element, or also called stiffness, okay, which is represented with K. Okay, right. So let us see. So this spring element is based on Coulomb friction. Okay, so let us continue the frictions. Third friction, say Coulomb friction, before going to the spring element. Okay, so we'll write so let us see the Coulomb. See here, the Coulomb friction is nothing but it is experienced when the body is in motion. Okay, and this friction is opposes the motion, but there is a very important point that the velocity, the magnitude of velocity and acceleration is constant in this friction. Okay, so see here, all right. It is experienced when the body is in motion. Okay, this friction opposes the motion but no dependence upon the magnitude of velocity or acceleration. Okay, acceleration of the body, which means what? This friction this friction consists of constant magnitude. Okay, so this friction is a constant magnitude, simply it is, right? Okay, now this is nothing but a Coulomb friction. Now we will see the spring element. So let us draw the spring element here. So this is a spring element. Okay, so here we have x1 of t displacement and v1 of t velocity, and here x2 of t and v2 of t, and see here external force is applied here, ft. Okay, so this is represented with k. Okay, spring constant or stiffness. Okay, so see here the k right. See here, it is concept of elastic. Okay, elastic deformation of of a body. Okay, so due to the spring element, okay, it is elastic deformation, right? So let us write the equations. Okay, let us write the equations here. Now see here, I will write directly. Okay, in terms of velocity. Okay, so in terms of velocity, you can see here. So the whatever the force applied, I can say spring force, okay, which is equal to K into see x1 of t minus x2 of t, right? So this can I written as x of t. Okay, so as we know, where I want to take x1 of t minus x2 of t is equal to x of t. Okay, so here we know that v of t is equal to d by dt of x of t. Okay, so this is a displacement, this is a velocity, right? Now this term I can write as so v of t is equal to k, the constant, d by dt of x of t. Okay, so this is a constant or compliance I am writing here directly of velocity, so no problem here. So see here, now x of t is equal to d by dt of x of t is equal to, so v of t divided by k. Okay, now expand this one, expand this one. So x of t is equal to 1 by k integration of vt dt. Okay, so here v1 of t minus v2 of t is equal to v of t. Okay, so this is the the force equation, I can say, right? The force equation is equal to force k is equal to 1 by k, the final equation I am writing integration vt dt. Okay, right. Second one is b in terms of displacement. Writing the equation in terms of displacement. What is that? Simply I can say the external force applied on spring element, okay, I am writing k, is nothing but, what is that? K into x of t. Okay, so I write this one, where k into x1 of t minus x2 of t, right? So where x of t is equal to x1 of t minus x2 of t. Okay, so these are the equations for spring element.